Hello, everybody. Welcome to your lecture number 24. We're going to be moving on to astronomy, and we're actually going to be finishing up the course with the next lecture, which will be on solar system. But today it's astronomy and the night sky. So we've looked at so many different aspects of the Earth so far, but now we're actually going to be settling and looking at the night sky and the changes that we see in the night sky throughout the course of an evening or a week or a month or whatever years. So before we even begin to get into the questions in your lecture assignment, things like that, I want to just show you some kind of a planetarium type thing, just to kind of give you a little bit of familiarity and background, because a lot of people are not really very familiar with how the stars move throughout the heavens. So before we even start looking at the lecture slides, I kind of want to just show you this website and give you an example of how the night sky changes. This is the planetarium website I like. There are many others, of course, on the internet, but this is kind of the one I'm familiar with. But so this would be Corpus Christi, tonight, which is in April. And if you look here, you can see this is to the north. You can see the N there at the bottom of the screen, and S there, that's to the south. And a lot of times the action you see here in Corpus Christi, and the night sky is going to be in the southern sky. And I'm going to kind of explain that in just a minute. But anyway, I want to fast forward right now and just kind of show you, generally speaking, how the different planets and how the stars move throughout the night sky. Okay, so I'm going to fast forward. This is showing it at 9 o'clock about, but I'm just going to fast forward it, and you can see that the stars and the planets, they all move together. Well, actually, that's not quite true, but all the stars move together, and they are spiraling through the sky, right? So I'm fast forwarding, it's 10 o'clock, and they're rising. You can see in the east over here. I'll point over to the east, and you can see that they're rising to the east, and everything is setting in the west. So it's not just the sun that sets in the west and rises in the east. It's everything. It's the planets, it's the stars, everything else. Okay, so those are all rising in the rising in the east, setting in the west. Okay. Now, I also want to point something out to you. So, this is why people in ancient times thought, you can just looking at the night sky this way, you can imagine how people in ancient times, because we're going to start off this lecture talking about ancient people and what ancient people thought about astronomy. So it's a little bit of history of science in this lecture. So anyway, I'm going to show you now, if we go to, instead of going throughout like number of minutes, we go through like a day, okay, in days. We're going to start cycling through days, okay. So actually what I want to do is first, I'm going to go back in time, and I want to get maybe, well, it'd be good if we could find Mars. Maybe we do this. Okay, we'll start going through time. So now we're going in, instead of minutes, we're going through days. Okay, so we're cycling through days, and you can see there's the moon going past and forward. Now I want to find a planet, and I want to show you what planets do. Okay, so now we're in July. There we go. There's Saturn. But what I'd really like is to have, and I'm going to turn the constellations on too so you can see this. Okay. What I'd really like to, though, find is something like Mars. And there we go. There's Mars. Okay. Now I want you to notice that all the stars basically move together. But I want you to take a look at what Mars does. Okay. And this is not just Mars, but all the planets, okay? And then I want you to ask the question, do the planets move with the rest of the stars? Because you can see all the stars kind of keep together in a one kind of whole shell, or what we call the celestial sphere. But what you're going to see is the planets don't do that, okay? So I'm going to start moving, and I hope that, again, we're going through the days. And what I hope you can see is that as we move through the days, Mars is moving. Now it's in Gemini, right? You can see, but before it was in Cancer, okay? It was in the constellation Cancer. So I hope that you can notice that Mars is moving. All right, so what this shows you is actually, it's not just Mars, but it's all the planets. They all move through the night sky. So I'll go back to the lecture slides now. And basically, the idea that ancient people got about the night sky and about the universe, they came up with the geocentric model, right? And the geocentric model said that the Earth was at the center of the solar system, and there's all these rings or shells of planetary motions and celestial motions around planet Earth. Okay, so that was the popular time, or the popular idea at the time of the ancient Greeks. Okay, so we're going to start off our discussion looking at the ancient Greeks. This is the golden age of astronomy, the age of antiquity. We're going to be looking at ancient Greek and Roman astronomers to start off with. And you can see that's your first questions that are on your lecture assignment, right, are about ancient Greek and Roman astronomers. So anyway, the ancient Greeks believed in this geocentric model of the universe, okay? And that makes a lot of sense when you look at the night sky like I just showed you, right? Because you see things moving through the night sky. You don't feel yourself moving, but you see the heavens moving. So it makes sense to think that, well, this isn't due to Earth spinning, which, you know, of course, watching things rise in the east and set in the west, it's actually due to Earth's rotation on its axis. But it's not due to Earth spinning, it's due to these things moving, you know, actually in these shells around the sky. So the ancients actually believed that there were 9 different shells around the Earth. So those 9 shells, you can actually count them. The first shell was all the stars, right? So you can notice how all the stars kind of move together, all the constellations move together in what we call the celestial sphere. The next was the moon. The next one was, of course, the sun. You know, and all those things move separately from each other. But then all the planets, they notice, you can imagine how strange this must have been for people in the ancient world to see that there were certain stars. Okay, I can see the sun looks different, obviously. The moon looks different, obviously. But then we see the stars, and there appears to be a few stars that wander around and don't follow the rest of the stars. And, of course, these are called planets. Planets, they didn't realize were anything, they just thought they were stars like everything else, right? They appear just to be points of light. They didn't realize that these were different than stars. So there were the different stars. Okay, Mercury, Venus, they could see, Mars, they could see, and they could also see, of course, Saturn and Jupiter. So if you do all the, keep track of everything, you see that there's these different shells that they thought were moving all separately from one another around the Earth. Okay, so that's the model. And I want you to just kind of keep that in mind as we go through the classical astronomers, because that's their worldview at the time. All right, so the first astronomer I want to talk about, of course, is, you can't get away from Aristotle. You really just can't overestimate how important he was for Western civilization, the Western intellectual tradition. But Aristotle, one of his contributions to astronomy, of course, he made many contributions to philosophy and to natural sciences, but one of his big contributions to astronomy is he realized that Earth was spherical. And I know that sounds maybe obvious to you. Of course, it's not obvious to everybody now. You can look and see that there are, especially on YouTube, you can find videos of people advocating for a flat Earth, right? And I've had students even who advocate for a flat Earth. But anyway, of course, that was a major topic of serious intellectuals at the time, whether Earth is flat or not. But he thought it was round, right? It was spherical. And he actually deduced that by looking at the lunar eclipses. So, you know, when you look at lunar eclipses, I don't know why my pen isn't working. I'm trying to get my pen to work here. Sorry, everybody. It's always difficult to get this to work. Here we go. Okay. So you see with lunar eclipses, you can actually see the spherical shape of Earth's shadow on the moon. And from that curvature, you know, Aristotle could tell that there must be a curvature to the Earth, because you could see Earth's shadow cast on the moon. So from that, he deduced Earth must be spherical. Pretty clever, I think. And he knew that Earth was round a long time before a lot of other people did. Okay, so And by the way, contrary to what a lot of people think, most, scholars and scientists of the medieval times and medieval ages did think that the Earth was round and not flat. So this was something that was basically in Western civilization believed, Earth was round for a very long time. This is 2,400 years ago, and pretty consistently even through the Middle Ages and into the age of the Enlightenment and the Renaissance. Okay, next guy I really want to talk about, who's just awesome. And I always look at this guy and amazed at how he was able to figure this out. But it's just ingenious. But this is Aratus. I always have trouble saying this guy's name. Eratosthenes. There we go. Eratosthenes, again, was a Greek, an ancient Greek, and was living in ancient Egypt at the time when he developed this experiment to measure the radius of the Earth and the size of this spherical Earth. So the way he did this was really clever. He lived in Alexandria, and he went down to Aswan, and he measured the angle at noon between the sun and the Earth. Okay, so he measured basically the shadow cast by the sun. He then moved up as fast as he could go to the city of Alexandria along the Nile, and he did the same experiment. He measured the angle between the Earth and the sun and the shadow that's being cast on the ground by the noonday sun. What he found is that there was a 7-degree difference. So knowing the distance from Aswan to Alexandria, he concluded that 7 degrees must be 1/50th of the size of the Earth. So, I'm sorry, I said that the wrong way. That distance between Aswan and Alexandria, 785 kilometers, must be 1/50th of the size of the Earth, the circumference of the Earth. Why 1/50th? Because 7 degrees, which is the difference he measured between the noonday sun angle in Aswan and Alexandria, is 1/50th of the size of a circle, right? There's 360 degrees in a circle. 7 degrees is about 1/50th or close to 1/50th of the size. If you do the math, get your calculator out, you can actually do perfectly Eratosthenes' math, and you can actually figure out that the Earth would have been, according to him, 39,400 kilometers in circumference. And that is very close to the current estimate of 40,075 kilometers. Very, very close indeed. I'm just amazed at how he basically nailed the size of the Earth. And this was amazing even more amazing because imagine that he didn't even know about the Western Hemisphere, right? Ancient Greeks didn't even know that there was a whole other Western Hemisphere and, the Americas, South America, North America, and all that. It was completely unknown to them. So it's just ingenious that they were able to come up with these numbers and just nail certain aspects, aspects of the Earth. Next guy I want to talk about here is Aristarchus. Again, a very famous and important astronomer during ancient Greek times. Now, he was one of the first people that, at least I know of, who advocated for a heliocentric universe instead of a geocentric. Now, he put the sun, instead of having it as one of the shells going around the Earth, he has the sun in the center and the different planets, and of course Earth included, going around the sun. Now, Aristarchus, even though he might have been a great astronomer, was just no match in terms of influence to Aristotle. So Aristotle's ideas of geocentrism won the day. So we're going to have to wait until the Renaissance to get to a revival in the heliocentric model. The next guy is Hipparchus. Hipparchus, again, another ancient Greek natural scientist and philosopher, who his great contribution was a catalog of stars. So you might remember, we talked about this in lecture number 1, what is science based on? It's based on empiricism. It's based on observation. We call it the empirical sciences for a reason. So Hipparchus was great because he was a great empiricist. He made lots of observations. He logged over 850 stars. He characterized them. He actually created a system for brightness that we still use today. We still use this Hipparchus system of magnitude of the brightness of a star. Also, he created a star catalog. He created the first, kind of put together the first maps of constellations and the night sky. He also created a method for calculating the date and time of eclipses. So again, these are all things that were going on more than 2,000 years ago. It's amazing. I mean, if I left it up to you, do you think without checking Google you could calculate and figure out the time of the next eclipse? We just had an eclipse, of course, here in South Texas. But could you figure out the next one? I bet you couldn't. I know I couldn't. So it's amazing that even as educated as I am, I don't know how to calculate the next date of an eclipse. But Hipparchus 2,000 years ago could do this and came up with a system for doing this. So again, just amazing. Another thing I want to show you here now, and we're going to kind of skip down to the bottom of the page here. I want to talk a little bit about retrograde motion. This was a really important thing for understanding why, kind of one of the main arguments for heliocentrism and against geocentrism. Okay, so again, there was this argument going on in astronomy for hundreds of years, thousands of years, about whether the universe is geocentric or heliocentric, right? Whether the sun is at the center or the earth is at the center. So I want to introduce this idea of retrograde motion. So retrograde motion is when there is an apparent reversal in the path of a planet in the night sky. So I'm going to play this for you, and you can get a little bit of this animation showing the motion of planets in the sky. So here's Mars, and Mars, over the course of days, there's Mercury. You see how Mercury goes backwards and then reverses course and goes forwards, okay? And you can see Saturn slowly crawling across the sky, right? And then it stops and it appears to go backwards, okay? So you'll notice that planets periodically will do this. If we go back, if I pause this and we go back to that planetarium, we can look at this again. Okay, there's Mars, and I bet if we just kind of go through the days, you see Mars moving through the night sky. Okay. And it starts to move the other direction, back to Cancer, right? And it's actually going to stop, and it's going to start moving back again, okay? So I hope that was clear for you. But that all is called retrograde motion. It's when the planet changes its apparent course, and it starts to move backwards relative to what it had been doing for the last, weeks or days. So that's called retrograde motion. Well, imagine that. That doesn't make very much sense. If the planets are just kind of slowly rotating around the Earth every day, how is it that they're going to stop, move back a little bit, stop again, and start moving in the same direction? So for a geocentric model of the universe, that's really hard to explain. For a heliocentric model, though, it makes perfect sense. Now, the last astronomer I wanted to cover from the period of antiquity tries to, I can say, reconcile geocentrism with retrograde motion. So you could see that the path of a planet changes over time. It'll start to retrograde, right? As you see in the time-lapse photo there. I think that's of Mars. Okay. So, So the last scientist I want to talk about is Ptolemy. Now, Ptolemy tries to explain retrograde motion by hypothesizing that planets undergo epicycles. So while a planet goes around the Earth, it's also simultaneously going in these spiraling orbits, like an orbit within an orbit as it goes around the Earth. And that's how he tries to explain retrograde motion. So Ptolemy's contribution, I can say, is maybe an anti-contribution, but he's trying to reconcile the geocentric model with retrograde motion, and he's trying to explain how retrograde motion occurs. Maybe I can say his real contribution to the advancement of astronomy is that he's trying to address the problem of retrograde motion and explain, and he's bringing it to the forefront of the discussion, trying to show and talk about how retrograde motion and geocentrism can both be true. Okay. Now, moving on, how did retrograde motion, how does that actually work? Doesn't have anything to do with epicycles. Ptolemy was not correct. What it actually has to do with is the motion of planets in the heliocentric model, right? The planets are going to, from time to time, overtake one another in their orbits. So let me show you this animation, and hopefully it'll make more sense. Okay, so you see Mars, and now we're going to start fast forwarding. Mars is moving, and then all of a sudden it will stop, and it will start to move in the opposite direction across the night sky. Okay, you can see the moon going back and forth, of course, because the moon is making these monthly cycles, right? So every 4 seconds, you're going to see the moon. Okay, now Mars continues its path. So what was that about? That was the retrograde motion. So roughly every 2 years, it says Mars appears to slow down, then suddenly move backwards against the night sky before it again stops again and continues on its usual west to east direction. Okay, that's known as retrograde motion. The reason that planets are called planets is due to this kind of motion. It's very erratic, and it doesn't follow the rest of the stars in the celestial sphere. So the Greeks gave the name to these special stars planets. Planets means wanderers. Okay, so that's the retrograde motion. What actually causes this? What actually causes this, we'll see, is when we have the planets going around the sun, and then one of the planets catches up to another in its orbit. So you can see here's Mars right here. Hopefully you can see that. Here's the Earth. And as the Earth catches up with Mars in its orbit, Mars will appear to reverse in its direction. Okay? So that's what is actually happening with retrograde motion. And it's explained perfectly by heliocentrism. All right, now moving on to the modern, and I say kind of modern, astronomers. So these are the astronomers of now the Renaissance and the Age of Enlightenment. So now we're fast forwarding out of the ancient Greek times 2,000 years ago, and we're going to maybe like 500 years ago or 600 years ago. Okay. So the first one I want to talk about here, these are the 5 we're going to talk about. And first one we want to talk about here is whoops, went too far, is Copernicus. Now, Copernicus was a Catholic priest, and he was also a natural scientist and a researcher and astronomer. And he used Aristarchus's his model and his observations, and Hipparchus's as well. So using ancient Greek data and observations, he argued for a heliocentric model of the universe and showed that a heliocentric model actually makes more sense. Now his work, of course, very influential, and we see now the heliocentric models start to gain ground. The next one after Copernicus was Tycho Brahe. Tycho Brahe was a Danish scientist. He had a science, astronomy observatory lab that was funded by the Royal Danish government. And he was able to collect very precise observations on the motion of the stars and the planets and the different celestial objects. So again, like Hipparchus, he was a great empiricist. He collected just tons and tons and tons of observations and data. And that was the data that gave his student, Johannes Kepler, kind of the everything that he needed to formulate his models of planetary motion. Now, Tycho Brahe also he had an interesting personality. He actually had you might notice in this picture, his nose looks a little bit funny. It's because he actually, in a duel, got his nose cut off in a sword-fighting duel. Which apparently, I don't know if this is true, but I read that it was a duel over who's a greater mathematician. So who a greater mathematician is, I don't exactly know. But who the better sword fighter was definitely not Tycho Brahe. So he lost the fight and he got his nose cut off. So the nose that you see there is actually a bronze prosthetic nose that you can still go and see today. It's in a museum somewhere. I don't know where, though. Anyway, his student, Johannes Kepler, was very important. Johannes Kepler was a German scientist, and he used all of Tycho Brahe's measurements to really nail down a heliocentric model for the universe. And not only that, but also developed 3 laws of planetary motion. So these are the Kepler laws of planetary motion, which are amazing because these are still true today. We still acknowledge that these are true today. And he was able to figure all of this out without Isaac Newton's knowledge. So Isaac Newton came later. We didn't have his laws of gravity. We didn't have his laws of motions. But Kepler was able to figure all this stuff out about planetary motions. Of course, he didn't even know what a planet was. He didn't know it was a rocky ball of, it was different than a star. But he was able to figure out these amazing laws of planetary motion based just on observations of how these things move through the sky. So let's go over these laws really quick. I know at first glance they sound really super hard and scientific, but I want to kind of break them down for you so they make it a little bit more digestible. First law is that planets move in an ellipse with the sun at one focus. So the thing about... So you might be wondering, what the heck is an ellipse? In case probably you saw this in a geometry class or something in a math class a long time ago, but you've probably forgotten. An ellipse is kind of like an oval shape. So orbits, planetary orbits are not circular. So our orbit around the sun is almost circular, but it's not circular. We have a time that we're closer to the sun. We have a time that we're further away from the sun. So we live on a planet that moves, and of course any planet moves in an elliptical shape. So ellipse is like a oval. Maybe the oval is the closest thing you can think of. And there are what are called two foci. Okay, 2 foci. So here's 1, here's 2. What's a foci? Or actually, singular is focus. What are foci? What is a focus? Basically, the way that you make this ellipse shape is that at any given point along this ellipse, the sum of D1 and D2, so that's the distance from focus 1 and focus 2, the sum of those is always the same. So you can see that here you have D1, you have D2, that's the distance from this point on the ellipse to this focus is D2. The distance from this point on the ellipse to D1 to this focus is D1. Okay, the sum of those D1 plus D2, it's always the same as you move around that ellipse shape. Okay, so the sun is going to be at one of the foci, and the planet's going to move in that elliptical shape around the sun. So you can see that if you put the sun right here, right, it's going to be a lot closer to the sun when it's here, that planet, than when it's over here. So your distance to the sun is always changing. I mean, that's true with Earth too. Our distance to the sun is constantly changing. The average is, about 150 million kilometers, but it's always changing. Now the second law is really weird too. Sounds strange. Hopefully the first law makes more sense now. But the lines connecting the planet and the sun, I'm reading number 2 right here. The line connecting the planet and the sun will sweep out an equal area in equal time. So I think the best way to imagine this is to look at an animation. So I like this animation a lot. It's, again, showing an ellipse. The red line is an ellipse. And what the person who did this animation did, they made all these like green and black pie slices. So those pie slices are all the same size, okay, in terms of area. So you're getting, with each of those pie slices, you're getting an equal size of piece of pie, okay? So you'll notice that as the blue circle moves around the red orbiting line, it's actually sweeping out those areas, those equal pie slices, in the same amount of time. And you'll notice that sometimes these things are really far away from each other, right? And other times they're really close, like right here and right here. And so what that means is that as you go around, and just pay attention, look at this, it's really good. Notice that as the planet goes around the sun, it's not going at an equal speed either. Sometimes it's going faster through its orbit than at other places. So when it's really far away from the sun, it's moving more slowly than when it's really close to the sun and it's moving faster. Okay, you can kind of see it almost looks like it's kind of getting slung around. Okay, it's going to start speeding up and accelerating, and it's going to swing around the sun, and it's going to deaccelerate and start accelerating again as it gets closer. Okay, the last law, the third law, is that, and again, this sounds really sciencey and mathy, and I'm sorry if it sounds complicated, but it's actually a really simple concept. It says the square of the orbital period, that's how long it takes to go around. I could even cross that out and say how long it takes to go around to orbit. Whoops. I'm sorry for all these little weird, little, see how these, I don't know what causes those horizontal lines. I wish I knew. But the square of the orbital period, that's how long it takes to go around the sun for a planet. So if you square that time, it's proportional to the cube. That means if you cube to the third power the orbit's semi-major axis. The semi-major axis is this. If you go from the center of the ellipse to the long, kind of the long dimension of the ellipse, that's the semi-major axis. So the time that it takes the planet to go around is going to be, I think it's just a really simple way to think of this. It's going to take longer for a planet to go around the sun if it's, maybe you can think of it further, well, I shouldn't say further from the sun, but if its orbit is larger. Okay, if it has a bigger ellipse, its elliptical orbit is bigger, its semi-major axis is bigger, it's going to take it longer to go around. And I mean, that's really intuitive, right? But there's even more precise, mathematical relationship between the two. But you don't need to know that. But I just want you to know that, like, they are connected with each other, okay? Now, the last scientist, or actually not, second to last I want to talk about is Isaac Newton. Isaac Newton, while he didn't maybe do a lot of astronomy, what he did do is worked on physics. And I want to point something out about Kepler before I move on from Kepler, is that even though Kepler formulated these amazing, planetary laws, planetary motion laws, he had no idea what powered the motion of planets through the heavens. That was a huge question, all the way back to Aristotle in the ancient Greek times. What makes these things move? They didn't know. And we didn't really have a good explanation for that until Isaac Newton. That's why Isaac Newton was just such a groundbreaking scientist. So Isaac Newton, you might know, formulated the 3 laws of motion. Okay, they're up there for you. You don't need to memorize his 3 laws, but it's like an object at rest. You remember this from middle school or high school physics, right? If object at rest stays at rest unless a Force acts upon it. Object in motion stays in motion unless a force acts upon it. That's number one. Number two, force equals a mass times acceleration. And number three, it's that third law, right? For every action, there's an equal opposite reaction, right? So, and then also the law of gravity. This is the law of gravity down here. He formulated the law of gravity, that the force of gravity, that's Fg, right? You see right here, is equal to a constant, that's big G, times mass 1 times mass 2 divided by the square of the distance between them. So that was an amazing thing. He figured out, this was the answer. He figured out this is the force that moves the motions through the heavens. And what's amazing is that you can actually take this. I know probably this won't make too much sense to you, but it's amazing. You can take Newton's laws of motion plus his law of gravity, and you can derive Kepler's 3 laws theoretically from his laws, from Newton's laws of gravity and motion. You can figure out Kepler's laws from Newton's laws. You can't figure out Newton's laws from Kepler's laws, but you can figure out Kepler's laws from Newton's laws. Or did I say that backwards? I'm sorry, but it's just amazing science. So anyway, Isaac Newton's big contribution, the law of gravity, and explaining why planets move the way that they do. The last scientist I want to talk about is Galileo. I'm sure you heard of Galileo Galilei, right? Famous Italian scientist, the first astronomer to use a telescope. Now, with his telescope, Galileo discovered some really interesting things. First of all, he pointed his telescope at Venus, for instance, and he found that Venus is not just a point of light. He saw that the planets were different than the stars. They weren't just points of light like the stars are. They are round objects, kind of like the moon. He noticed that Venus has phases, just like the moon has phases, and that therefore it must be orbiting around its source of light, heliocentrism. He also noticed that Jupiter has moons of its own. So that means that Earth isn't the only game in town. There are other objects in the sky that are orbiting around other objects in the sky. So it's not like everything orbits around the Earth. And that kind of showed that the Earth isn't the center of the universe, right? Other things are orbiting around the Earth. Other things are orbiting around other things. There are moons of other planets orbiting around other planets, right? So that kind of was the nail in the coffin to disprove geocentrism and move on to a heliocentric conception of the universe. Okay, contrary to the misconceptions of many people, Galileo wasn't burned at the stake for this, but he did get in some trouble with the church, and he got under house arrest, I believe, if I'm not incorrect about that. So. But he wasn't burned at the stake. Not saying that scientists weren't burned at the stake, but Galileo wasn't. So one thing I wanted to talk about too, a little bit more, is about constellations. So constellations are clusters of stars. We have right now 88 recognized constellations, and constellations are great because they help us map out the night sky. Okay, so when you look at the night sky, you can kind of figure out where you are in the night sky based off of what constellations you see. Okay, I think the easiest here in Corpus Christi to see is if you look in the southern sky, it's usually pretty easy to find Orion and Orion's belt. So if we go back here to, I want to go back to. So here are the oh wait, no, I don't have it on yet. Here are the constellations, okay? And I'm going to change it back to today. Oh no, it's today's date. So usually if you go and you look to the south, That's where you usually see a lot of the action. And it's usually pretty easy to see Orion. On Orion's belt, especially, it's like 3 stars, pretty bright stars in a row. And there's also Rigel and Betelgeuse, which are also pretty bright stars. And the brightest star in the sky actually is usually Sirius right here, which is part of Canis Major. Okay, and if there can be stars planets that are brighter in the sky often. So like Jupiter. So if you look over at Jupiter, you'll see that usually Jupiter and Venus are going to be the brightest objects in the sky. But of course, that depends how close they are to the Earth, right? If Jupiter happens to be closer or Venus happens to be further away, that can change their relative brightness. But normally, if you look out, the brightest things you see in the sky are either going to be Jupiter or Venus or Sirius, okay, which is part of Canis Major. But I think this is the easiest. Orion's the easiest constellation to see. Now, I do want to show you that if you go look to the north, I want to look at a very special star, and this is Polaris. Polaris, okay? Polaris is very special. It is the North Star, and our axis of rotation points directly at Polaris. So that means that unlike everything else in the sky, which kind of like rises in the east and sets in the west, Polaris never sets. It never goes down. You can always see, as long as you are in the northern hemisphere, you can always see Polaris. If you're in the southern hemisphere, you can't see it. Okay, so I'm going to fast forward through time and show you that as we go through time, everything is zipping around, counterclockwise around Polaris. Polaris is part of Ursa Minor, part of the constellation Ursa Minor. If you want to find it, I think there's a few different ways. The Big Dipper, which is actually the constellation Ursa Major, you can see it here. This is the Big Dipper right here. The Big Dipper usually, if you kind of take a line right here between this, there's Ursa Major, right? Kind of the tip of the ladle of the dipper points directly at Ursa Minor and at Polaris. Okay, so that's kind of the way I find it in the night sky. There's a lot of different ways. So anyway, Polaris is in Ursa Minor. Another thing that you should know about Polaris, it's really important. If you are in Corpus Christi, our latitude is 27 degrees north. That means if you look 27 degrees above the horizon, so 90 degrees would be straight up, 45 degrees would be like in the middle, 0 degrees would be like the horizon. Okay, if you look 27 degrees, you will see Polaris. So Polaris actually tells you what your latitude is in the northern hemisphere. So you could always figure out, if you were like lost and you didn't know where you were in the northern hemisphere, you could always know your latitude by knowing where Polaris is. Okay, it's also really cool because it can tell you it can tell you so many things. It can tell you also like what season it is. It can tell you what time it is. You can figure out a lot between like the angle between the Big Dipper and Polaris. So they're really useful constellations to know about. Okay, so I'll move on here. So you notice how everything rotates counterclockwise around Polaris. Almost everything in the solar system rotates counterclockwise. Okay. So I wanted to talk a little bit about that, about Earth's rotation around the sun. You have to remember that the way that we keep track of days, we keep track of days using Earth-Sun geometry, right? When the sun comes up and then it goes down, for us, that's a day, okay? And we say that there are 365 days in a year, and a year is how long it takes for us to go around the sun. The problem is that it's not exactly true. So you have to remember that it's a little bit tricky to use the sun to keep track of a day while we're simultaneously going around the sun. So while we go around the sun, we're also spinning, right? And what ends up happening is that our position changes every time we go around. We continue on our pathway around the sun. Our position changes slightly, and that's actually going to change how it's going to change the way we keep track of days. So a very common way that astronomers keep track of days are not using the sun, what we would call a mean solar day. They actually use something called a sidereal day. A sidereal day is the time for a given star to appear in exactly the same position in the night sky. Okay, and that's actually tells you how many actual rotations that we do as we go around the sun. Now, you know that this year is a leap year, okay? Maybe if you're watching this next year, it's not going to be a leap year, but this year that I'm in right now, it's a leap year, right? And we have to have leap years because of the fact that sidereal days are not the same as mean solar days, okay? There's actually a 4-minute difference, and those 4 minutes add up, and over time, we need to have a leap year to kind of reset things and keep them on track, okay? Because we actually don't do 365 full rotations during the course of a year when we actually go completely around the sun. Okay, so anyway, I want to just show you this. What is the ecliptic plane? The ecliptic plane is very important. The ecliptic plane is the plane that contains our orbit around the sun. It's also, when we look in the night sky, it's the apparent path of the sun against the celestial sphere. So I kind of want to show you this here. We'll go back to our stellarium, and I want to show you, I can turn on the ecliptic plane. I'm going to turn on the ecliptic line right there, okay? And then you can see there's this red line called the ecliptic line, okay? And this is actually the intersection with our ecliptic plane with the night sky, okay? So if I zoom in and kind of, I'm going to make the look to the east, I'm going to look to the east, and I'm going to let the sun come up, okay? So I'm going to zip through the hours here, and you'll notice that the sun's going to come up along and follow the ecliptic line. But I want you to notice that also it's not just the sun, but I want you to notice as we go through the night, all of the planets follow the ecliptic plane too. And the moon follows the ecliptic plane too. Yeah, not exactly, but almost. You notice how over here, Uranus, Jupiter, and the moon, they're all basically on the ecliptic line. And that's because everything in the solar system is orbiting in this same ecliptic plane. Okay? So ecliptic plane is a very important thing. You know that our rotational axis is tilted 23.5 degrees relative to our ecliptic line. Okay. So here's the perihelion and aphelion. So you know that because we have an elliptical orbit, sometimes we are closer to the sun and sometimes we're further away from the sun. When we're closer to the sun, we call it the perihelion. When we're further from the sun, we call it the aphelion. Okay. I did want to talk a little bit too about the moon. So how long does it take for the moon to complete an orbital period? Now, this goes back to this whole thing about sidereal days and versus mean solar days. And the same thing with the moon. We call it a synodic month versus a sidereal month. You know that on average it takes about a month for the moon to go around the Earth. However, there's a difference between a sidereal month and a synodic month. So I might ask you, how long does it actually take the moon to go around the Earth? And the answer to that is it takes 27.5 days. That's a sidereal month. That's how long it actually takes the moon to actually go around 360 degrees around the Earth. However, you know that the moon goes through phases, right? Full moon, new moon, quarter moon, blah, blah, blah. It actually takes 29.5 days to go through that list of phases, that series of phases. Why? It's because simultaneously as the moon goes around the Earth and the moon are also going around the sun, and that changes our position relative to the sun. And of course, if we're keeping track of the days using the sun, that's going to throw everything off. So in reality, it takes 27.5 days for the moon to go around the Earth. And that's a sidereal day. That's using the stars to keep track of things rather than the sun, which throws everything off because we're going around the sun as we try to keep track of Earth-Sun geometry and Earth-Sun-Moon geometry. So it throws everything off that way. Okay. So there you go. There's the different phases of the moon. The new moon, we see that during eclipse, which actually, as of recording this today, was yesterday. We had our major South Texas eclipse. That's the only time you ever see a new moon. Okay, a new moon is, otherwise you don't see it. Okay, it's when the moon is basically right in front of the sun like that. And then when you see a moon that looks like this with the right-hand side of it illuminated, that is called a first quarter moon. Okay, we don't call that a half moon. Never say half moon. The half moon isn't a thing. It's called a first quarter moon. That, of course, is a full moon. You know that. That's when the Earth, moon, and sun are all in a line. And basically, you can think of the moon as behind the Earth. Okay, that's when we're going to get lunar eclipses, which we sometimes get, and Earth's shadow is cast onto the moon. That happens more frequently than we get a solar eclipse here in South Texas. You can sometimes see the full moon near the horizon when the sun comes up or it's going down. You can see the full moon at day when it's very close to the horizon. Now, after that, we'll get a third quarter moon, which you'll notice now the left side of it is illuminated. And then finally, after that, we'll get a new moon again. Sometimes you'll notice that the moon appears orange. There can be a few different reasons for that. Sometimes the moon appears orange like this when it's close to the horizon. And that's because when an object is close to the horizon, its rays of light are going through progressively thicker layers of our atmosphere. And that scatters different wavelengths of light differently than if it's going through a thinner slice of our atmosphere. So a lot of objects, like the sun, of course, sunsets, appear this kind of reddish, yellowish, orangish hue when they're close to the horizon like this. Sometimes, though, you can have lunar eclipses, and that can change the color of the moon as well. It can make it appear blood red for a little while as the Earth casts its shadow on the moon. So what do you think of this? Do you think, is this the moon? What do you think? Is this the moon? Or is this Mercury? Or something else? So this is actually our moon. It's the dark side of the moon. It's the part of the moon that doesn't face us. So our moon is in a gravitational lock with Earth. So they rotate together like this. And because they rotate together like this, we only ever see one side of the moon. So we never see this lovely backside. But no, I think that actually we get the prettier face of the moon, right? So that's the face of the moon that we're used to seeing. Okay. So we don't get lunar eclipses every month. That's where the Earth's shadow is cast onto the moon. We don't get that because the moon's orbit around the sun is actually tilted on average about 5 degrees. So we're not in perfect alignment with the sun and the Earth. So the sun, Earth, and moon are not in perfect alignment most of the time. Otherwise, if they were in perfect alignment, we would get, a lunar eclipse every month. Now, a solar eclipse is different. Solar eclipses are when Earth's first of all, a lunar eclipse is when Earth's shadow is cast on the moon. A solar eclipse, like we just had this yesterday. A solar eclipse is when the moon's shadow is cast onto the Earth. Okay, so usually in a particular area, you're not going to be lucky enough to see a solar eclipse. Whereas a lunar eclipse are more frequent. You'll usually get a visible lunar eclipse at least once a year. So anyway, I've gotten through everything. Sorry, this is one of the longer lectures, but I hope you enjoyed it. Please let me know if you have any questions, and I will talk to you next time. You have a great week.